This is Rosen Discrete Mathematics and its Application, section 9.4 on solving congruences. We're going to talk about a very important theorem called Fermat's Little Theorem, and I use the lowercase abbreviation of it to distinguish it from the more popularly famous Fermat's last theorem, which is the subject of much research and literature in mathematics over the past couple of centuries. But Fermat's Little Theorem is very useful in the realm of computer science and number theory. And it states that if you have a prime modulus p, okay, I'm going to get my pen working again. If you have p as a prime modulus and an integer that is not divisible by p, then a raised to that prime minus 1 is congruent to 1 mod p. And of course, if I multiply both sides of that by a, I get a raised to the p is congruent to a mod p. And again, p has to be prime and a has to not be divisible by p. Okay, let's take a look at the application. Basically, this allows us to compute very large exponentiations under moduli, even faster than binary modular exponentiation. Of course, it requires that the modulus be prime and that the number being raised to a power is relatively prime to the modulus. Now we want to find 7 to the 222 mod 11, and since 7 and 11 are relatively prime, 11 is prime, I know by Fermat's Little Theorem that 7 raised to the 10 is congruent to 1 mod 11. So however many 7 to the 10s I have, I can set them equal to 1 and find the solution. So 7 to the 222 is 7 raised to the 22 times 10 plus 2. I can rearrange those to say 7 to the 10 raised to the 22 times 7 squared is, and then all of these become a 1, giving me 49, which is congruent to 5 mod 11. So the remainder of 7 to the 222 and divided by 11 is 5. Okay, Fermat's Little Theorem has very important application in an area called pseudoprimes, which we take advantage of to find large prime numbers, or probably large numbers that are probably prime. Okay, so if I'm looking for a prime number, let's say n is the number I'm wanting to check. If n is not 2, and 2 will be relatively prime to it, by Fermat's Little Theorem, 2 to the n minus 1 should be congruent to 1 mod n. So if the congruence holds, it may not be prime. If n is prime, it will hold, but if it holds, it doesn't mean that n is prime. If we have compositive integers n such that 2 to the n minus 1 is congruent to 1 mod n, they are called pseudoprimes to the base 2. Here's an example. 341 is not prime. However, it appears to be prime because if I raise 2 to the 340th power, it is congruent to 1 mod 341. How do we do that? Well, we use binary modular exponentiation to check the result, 2 to the 340 mod 341. So 341 we would say is pseudoprime to the base 2. It is not prime. Now we could replace 2 with any integer b, and in doing so we say that if an n is a composite integer that satisfies b to the n minus 1 is congruent to 1 mod n, then n is said to be pseudoprime to the base b. Of course, if n was prime and b wasn't divisible by n, we would use Fermat's little theorem to get that result. Okay, now how can we use this to find large primes? Well, here's our relationship again. Looking for a prime number n that satisfies 2 to the n minus 1 is congruent to 1 mod n. If n doesn't satisfy that congruence, it is composite for sure. If it does satisfy the congruence, it might be prime, or it might be a composite that is pseudoprime to the base 2. How likely is it that it is one versus the other? Well, let's take a look. Among all the positive integers less than 10 to the 10, 455 million of them are primes, but only less than 15,000 of them are pseudoprimes to the base 2. So if I find a number that satisfies this congruence, there's a 99.998% chance that it's prime and a very, very small chance that it's pseudoprime. So that's how we can probabilistically find large prime numbers, is we check them against to see if they satisfy the Fermat's little theorem congruence. If they do, we will conclude that it's more likely prime than pseudoprime. Then we can do additional tests with other bases besides 2 and get more evidence as to whether or not a particular large number n is prime. And for more descriptions of finding large primes, then we say probabilistically, there's an exercise in this section and another exercise in section 7.2.